Hey everyone, my name is Luke, and I'm working on a new game called Firetale. It is a procedurally generated strategy RPG game. I'm really excited about it. What I want to do today is just try a shot at creating a video tech blog, really a dev blog about some stuff that I'm working on for the game. This time around, I just want to talk about the basics of the procedural generation that we're using for the map itself, actually. So let me just jump right into that. There is an associated like text blog post on itch.io that you can also read if you're interested. It probably goes in depth to slightly different things, but really this video is related to that. So just jumping right in, let me show you the basic setup of the project in Godot here. So um, at the high level, I really just like to have a controller node up at the top. This gives me the ability to swap in and out different nodes underneath it, like a game node or a menu node or a pause screen node or whatever I need, um, without having to mess too much with the scene tree itself. It makes life a lot easier. Over here, we have a game scene. This is really just me playing around. I think this looks kind of cool. We're using a third-party tile set here for the hex tiles right now. I think they look great. You can check out the link in the blog post or in the video um, to see what tile set we're actually using for that. Might honestly just stick with it for a long time for this game because I think it's really cool. But over here, we have the game scene. So let's talk about that. You can see in the controller, the game scene is actually a child node of the controller. Game scene here, we have our tile map, which is a hex tile map, and you have to do some tricks um, to do hex tile maps in Godot, but it's not too tricky. And then we have our camera, which handles zoom and panning and all that. And I'll probably do another blog about that in the future. There's a lot to it, and there's a lot of room to enhance that functionality in Firetale, but we have what we need to actually, play around so far. As far as scripts go, and this is really what I'm trying to get at here, is we have a top level game script. This script really handles all of the input. So it handles um, input events, and it emits signals when it detects particular events. Again, I'll get into that more in another post. We have our utilities in here right now. We just have dictionary utils. Um, I'll talk a little bit more about this method when necessary, but it's just a static utility method. I don't need to instantiate this class anywhere to use it. Um, I can just call dict utils dot filter compare, and I'm good to go pretty much anywhere in code. And then finally, we have our map service. This is a singleton, and this is where we're going to spend most of our time talking. The one thing that I wanted to point out with this guy is that in project settings, I actually have map service set up as an auto load. So that's what makes it a singleton in the realm of, Godot game development. So I actually like to edit code for my Godot projects in Visual Studio Code. I think the code editor is just way better. So I'm going to pop over to that for now, and we can see what is going on here. So really, I went through a couple of different strategies for basic procedural map generation, and I'm sure I'll go through a couple more as I continue to play with this game throughout its development lifecycle. What I landed on was a three-tiered process, and there will be more tiers in the future. There's more stuff that needs to be generated, but as of now, there's a three-tiered process. Tier number one generates the biome. So this is how you say this part of the map is desert. All of this is, grasslands and forest and stuff. Over here, maybe it's like Arctic, icy, snowy, whatever. Maybe another desert down below there, stuff like that, right? So at the first part of this script, we basically just define a bunch of our biomes. Desert, grassland, and snow are the three that we have right now. The second phase of generation actually dives into terrain. So this is how we decide on a biome what actual tile should be shown, essentially. Should it just be a plain tile, a grass tile, for example? Should it be a lightly forested tree tile? Should it be some foothills? Should it be forested foothills, mountains? Should it be a town? And so on. Obviously, I have water in here as well. Um, cool thing about terrain is it really, each of these tiles kind of correlates to altitude, if you will, in a world, apart from maybe the town tiles, right? So if we can procedurally generate altitude, then we can create some pretty natural flowing worlds using these tiles. You know, generally you'll go from plains to a little bit of forest to some foothills to some mountains. You know, in real life, we can emulate that with procedural generation pretty easily. I have some constants defined for keys in my dictionaries here. This just makes sure that I don't have stupid typos that make it really painful to debug an issue in the future. Um, town criteria. So kind of what I was referencing earlier in dictionary utils, I created a little bit of this like filter function, right? So what this allows me to do is pass in a dictionary. It's a dictionary. You can think of it like a JSON object almost, if you are unfamiliar, or like a map if you're coming from like a Java or a Golang or something. Um, and then we have an array of criterias, which is really an array of dictionaries as well. And what we do here is we actually loop over all the criteria documents or criteria dictionaries in the criterias array. And for each one, we make sure that every single key that it provides the value for is also in base and has the same value. If it's not, then we ultimately fall out and return false. This base document does not match the criteria specified here. If we are good at the end of it and we have no mismatches, one of the criteria actually hits, then we return true. So I kind of describe it up here, but the gist is that within a single criteria dictionary, each key is ANDed together. Okay. Then every criteria dictionary itself is actually ORed together. So you can kind of say, hey, I want a map, or I want to know if this dictionary either has field A equals 1 and field 2 equals B, or I want to know if it has similarly field, you know, C equals 3. I know I mixed letters and numbers up there, but hopefully you get the point. So over here in the map service, really what we're defining here is a criteria array, an array of criteria dictionaries that basically define what a town object or a town dictionary actually looks like. Hopefully this makes more sense as we get into it. I then defined a bunch of threshold values here and a bunch of lookup tables. Really, I had all of this hard coded initially down below in the actual code, but it made more sense to just make it very configurable, especially because the end goal for Firetale is actually that when you create a new game, you can kind of tweak these values yourself if you really want to get crazy, right? So I won't get too much into what the thresholds mean. I think it's just important at this point to note that I have lookup tables of threshold values to biomes. And then similarly down here, I have lookup tables of basically it's a biome threshold value to terrain. And some biomes, as you can see, actually don't even care about some terrains, right? In my world, we're not really putting trees in the desert. I'm sure that exists, you know, but we're not doing that in Firetale right now. Up here, this lookup table, it's, I think the last lookup table I need to describe, really just shows a mapping of biome to each terrain that it supports. Some of them don't support a particular terrain, like desert doesn't support forest. As you can see here, we set it to null. Mapped to the position in the actual tile set that the tile for that terrain, for that biome exists. So I'll give you an example here. Let me switch back to Godot real quick after we pick one of these. Let's just choose foothills. So for the grassland foothills, the tile is at an x coordinate of 3 and a y coordinate of 0. So if I switch back to Godot here, we can actually pop open that tile set. I'll zoom in a little bit. And there's probably a better way to do this, but the best way I have is to count, right? So a y coordinate of 0 means that we're on just this first row here, right? And then an x coordinate of 0 actually means that we are at, or I guess of 3 means that we are at 1, 0, 1, 2, 3. So those are our foothills right there. Okay. Let's get back to VS Code. So over here, if we just keep going down now, we have a couple member variables here. We have size, which literally holds the size of the map that we are generating, just a vector too. So, x is width, y is height. Town chances and town spacing. So these are used later. Town chances is used to basically determine how many rolls, how many sides of a die that I'm going to roll exist, so that I can determine whether or not a particular position in the map should actually have a town instantiated. Town spacing is used for a rule down below. We'll talk about that again in a little bit. Really what that means is no two towns can be within 5 spaces of each other at its core. And then finally, we have a map object or map member variable right here. This is actually a 2D array. Godot just doesn't allow me to describe that here. And the first dimension is the x coordinate, second dimension is the y coordinate, and the value at each one is a dictionary holding data actually about that position on the map. If I just scroll down here really quick, in Godot, I actually have to do this weird initialization method to create a two-dimensional array. When this is called, first we blow away everything in that member variable, and then we make sure that we actually are built out to the appropriate size, x-wise, and then for each x column, I guess, we then append a empty dictionary object in each y row of the map. So that gives us a good basis. That's a good assumption. Initially, when I did this, I thought about just appending, a dictionary lazily upon access of a coordinate in the map, probably down in this method down here, update map. But in reality, I think that would be less performant, because that would mean that rather than just doing this once at the beginning of generation and getting it over with, every single time that I want to update a position on the map for the remainder of the game, I would have a couple of conditionals, if statements in here, to see if I actually needed to do this. Because I do this here, I can just assume that at every position after the map has been initialized, there is at least an empty dictionary there, which means I can really simply modify values with a statement like this. Okay, so we have a couple getters down here. Get size just returns literally just the size. Get subtile, this returns for a given location on the map the actual tile from the tile map or tile set that we just looked at in Godot that should be shown at that position. I won't talk too much about that. I hope it's self-explanatory. If not, let me know and I can explain a little bit more. The entry point for generation is map service.generate. So in here, we take in a size. Eventually, we'll also take in seed values and stuff like that. Kind of like how you might in like Minecraft or a different game like Terraria or something like that. We call that initialize map function that I was just talking about. And then we go through all of our generation phases. So generate biome, generate terrain, generate towns. We'll talk about each one of those a little bit. So in generate biome, we're using a gradient noise map for generation. What that means is we use this open simplex noise implementation, which is actually just a built-in implementation of the open simplex noise algorithm in Godot. It's pretty sweet that I didn't have to write anything myself or find a third-party library. We give it a few values here. These are really things that you can tinker with, right? Octaves it's really how many layers of noise do you want? Period is my understanding of period is what is the base frequency that you actually start oscillating off of um, when you're generating noise. And then noise persistence says for each of those layers, how much weight is applied to each of those layers when they're flattened down into a 2D noise map, right? So zero point 0.5 is actually the default, 3 is actually the default, 20 is not the default, 20 is much less. The default is 64. I found that if I tweaked these parameters in certain ways, I would get really blotchy biome output from this phase. I might have like a single desert tile and then a single grassland tile. So my goal with this was actually to get more just really smooth and slow, really hills in the noise map that came out. Um, if you don't know what a noise map looks like, a quick, Google image search would probably help this all make sense for you. Uh, Down here, what we do is we actually essentially we iterate over the width and height of the actual map that we're generating, and for each position in the map, we grab a noise value. I do a little bit of debugging logic here. I actually keep track of the minimum and maximum noise values that I get. I found that at least on my machine, I hope it's standard um, everywhere, but on my machine, I often would get more values closer to zero and less values at the edges of the noise map's value range, which is -1 to 1, I believe. Um, and then basically,
My apologies. I couldn't hear what you said.
Siri's trying to talk to me here. Um, Finally, down here, really what we do is we loop through those thresholds that are defined in that lookup table up above that we were talking about. And for each threshold, uh, we basically compare the value that we got out of the noise map, right? So if the value that we got is less than the defined threshold, um, then we assume the biome associated with that threshold in the lookup table is the biome we want to assign to that position on the map, right? Um, the important thing with how this works is that in that lookup table, we can even go back a little bit, we define our thresholds in order of least to greatest, right? That's just how that algorithm that I have down there is written. We could do it, greatest to least. We just have to flip our greater than or less than sign to the opposite of what it is. So that's really all it takes to generate the biome itself. One thing I kind of glossed over here was the randomization. Randomize should not be called here. We should be calling randomize somewhere at the top of the actual game itself once. Really what that does is it properly seeds the actual game random number generator so that you don't just every time you run the game you get the same generation otherwise. This is gives me a random integer that I can seed the noise generator with. All right, moving on. Generating terrain. To be honest, we generate terrain the exact same way that we generate biomes. The only difference is we tune it a little bit differently. So we wanted a bit faster, um, still smooth, but faster oscillation in the noise map that we generate. So this tuning seemed to feel pretty good when we did that. Um, Down here again, iterate over each position on the map, get a noise value, and then we basically just do the same thing. We figure out which terrain tile for the biome of the threshold or of the position that we're on uh, is within the threshold that we are um, basically at with the noise value, right? So uh, some interesting things with this, I can even scroll up to the lookup table for these and we can talk about it a little bit. I found that when I was generating, terrains initially, it was actually back when I only had one generation step. If I did things like put uh, water all on one side of something, which I do here because it actually works out pretty well. But if I put water all on one side of something, then it will only ever touch that thing. Like in this case, water will really only ever touch the planes. Okay. That's okay because my threshold value for plane and water is actually basically the same for all of these. So I actually get kind of cool looking maps where water can span different biomes and stuff like that. Um, the other thing that I tried initially was putting water in multiple different spots, at multiple different thresholds within this map. Um, and you can do some cool stuff with that. I'm not doing it here, but if you think about it, what that actually gives you is almost like an island type world where your plains and maybe your forests are surrounded by water. You know what I mean? Um, Kind of cool. Probably something that we'll want to expose in Firetale at some point. The final generation that we do right now is town generation. And this one's actually, I personally think this one's a lot simpler than the noise generation ones. Again, what we do for towns is we actually loop over every single position in the map. And the first thing we do is we call this is town allowed method. And what is town is allowed does is it basically it goes and looks at every tile within the town spacing member variable, which is set to 5 right now. So 5 up, around 5 to the right, 5 to the left, 5 down. Um, and make sure that the rule that we have defined in town criteria basically applies. So really what we're trying to figure out here is if any of those tiles within that 5 position distance from the position that we're considering putting a town on has a town already, we want to skip this. We don't even want to try to put a town on this tile because that's too many towns. The next thing that we do is we essentially just roll a die. So town chances, I believe, is set to 500 right now. And in here we really just roll a 500 sided die, and then we say, hey, if it's greater than 499, that's town number one. That's town type number one. If it's greater than 498, town two. Greater than 497, town three. Greater than 496, town four. And then finally, if nothing in those four values got rolled, if we got one of the other 495 values on the die, then we really don't do anything. We leave the terrain as is. All of this ultimately gives pretty cool looking maps. So if I come back to Godot and I actually run this a couple times, and I'll go to the Firetale thing. So here we have a map where you can see we generated a town here, some plains and plateaus up here. The plateaus are like the mountains in the desert. Down here, just some Arctic biome surrounded by icy water. Down here, we have a little bit of a more desert. Cool thing is, as I'm doing this, I don't know what I'm looking at either. This is what's exciting about this, and what I think will give Firetale a lot of replayability is every generation is going to be so different. We'll do one more after this, just so y'all can see. A little really plainy desert over here, some more towns, a tower, some foothills. You get the picture, right? Um, I'll actually go ahead and restart it again and we can see what we get next time. So this time we got, looks like a big plain here in the middle. We got a little Arctic area right here. Another Arctic area over here. Some towns, a little tower over there. Um, Kind of a cool little desert with some foothills over here, some mountains over here. Um, yeah, just like it's different every time, and really I think that the way that the algorithm, the generation algorithms have been tuned so far, and really that's what a lot of my tinkering has been with is those tuning values. It generates pretty cool looking maps. Um, I'm at the point where a lot of what I run into is pretty cool to explore. And I'm excited to start adding content to each of these tiles. And the idea is that that content will actually also be procedurally generated. So again, like every layer of Firetale will be pretty dang unique. That is really all I had. That was a bit of a long one. Probably too long, I'm not sure, but that's the first video devlog. So hopefully you all enjoy. Let me know if you have any questions. Hit subscribe on the channel. Check out my Twitter. Look at itch.io. That's probably where I'll continue to post, text style blogs about this stuff. And we'll get you some more updates soon. Thanks for watching.